This video is part of an online course on algebra and will be about the cardinality of sets. Way back when we were a little kid, if somebody asks you to count a set of stones or a set of blocks or something, what do? Well, you would do something like this: 1, 2, 3, 4, so on. This is the same thing the bank teller does when you ask him to give you a bunch of notes. He riffs through the notes 1, 2, 3, 4, 5. That's how you count. So essentially what you are doing is, to each object that you want to count, you are assigning an incremental natural number. So you start with 1 increment, the second one is 2, 3, 4. When you have exhausted all the things that you need to count, the number you said last is the number of objects you have. Today we are going to do the same thing, but in a way more abstract way that most toddlers will not be able to understand. We want to now count the elements of an arbitrary set. Well, how do you do that? Well, start with a set S. We say the set has n elements, where n is a natural number, if there is a bijection between the set S and the set 1 to n. This was also called, we use a different notation also for this. This is 1, n, the initial segment from 1 to n. Now this is exactly what the toddlers do, what we have all done when we were kids, just pointing to objects and counting. So this definition should not be very surprising, it should be natural, and certainly any toddler will be able to understand this. Now it can happen that the set S is empty. In that case, we say the obvious thing, we say S has 0 elements. We say the set S is finite if S has n elements for some choice of n. Here actually we allow n to be 0 also. So a finite set is either empty or bijective to some initial segment 1 to n. Now in this event we say that the cardinality of S is n, and we give a notation. We write something like absolute value modulus of S equal to n. This is to be actually read as the cardinality of S, or the number of elements of S is n. Otherwise, if it is not possible to find a bijection from S to any initial segment 1n and S is non-empty as well, then we say the set S is infinite. Now cardinality is just a fancy word for number of elements. Don't get too bogged down by it. We say two sets have the same cardinality. Here S and let's say P are two sets. They could be any two sets, they could be completely complicated. We say they have the same cardinality if there is a bijection between them. What does that mean? This means that to each element of the first set, there is associated exactly one element of the second set. That means we can pair together points in the first set and the second set. So they do have the same number of elements. That's why we say two sets have the same cardinality if there is a bijection between them. All this should be fairly obvious to you. We are just doing things in a more abstract way, that which we have been doing for at least a dozen years. We have this following obvious fact. So in this particular video, a lot of stuff is just straightforward. So I will leave a lot of stuff for you to do on your own. So if you have a subset of a finite set, then it is finite, and any superset of an infinite set is infinite. Now both these statements, both about subsets and supersets, should seem completely trivial and obvious to you. Nevertheless, there is something to prove, and it is instructive. So I suggest that before you proceed, just pause the video, spend maybe 10-15 minutes and write down a fully rigorous proof that a subset of a finite set is finite and a superset of an infinite set is infinite. Okay, I will not do this proof because it's fairly easy, but it's still something that you should do once in your life. Okay, I hope you have managed to prove that a subset of a finite set is finite and a superset of an infinite set is infinite. So let's move on. We come to yet another obvious fact. This fact is repeatedly used in mathematics in strange and surprising ways. It's called the pigeonhole principle. You have probably encountered this in school. If you have not, it's not such a big deal. This says that if m is greater than n, then there is no injective function from the initial segment 1m to 1n. That is, if m is greater than n, you can't find a bijection from 1 to m to 1 to n. This is again a fact that seems completely obvious. How is it possible to pair off one element in the initial segment 1m to one element in the initial segment 1n unless you double count? It's not simply not possible. Again, you should pause the video and write out a rigorous proof. It's not more than a few lines long. It's fairly easy. But rather than me doing it, it is very instructive if you do it, because you will have a better understanding of what is to follow, because some of the proofs that are going to come a little bit later in this same video are not so trivial. So this is sort of a warm up for your brain. Okay, I hope you have managed to prove this, and also maybe in the process of proving, this question came to you, why is this called the pigeonhole principle? Well, first of all, observe that this initial segment 1 to m and 1 to n are just for concreteness. In a more abstract sense, this says that if you have a set S which has m elements, so let me write that down. If you have S with m elements, and let's say a set P with n elements, then you can't find an injective function from S. So typically injective functions are written like a hook. So this is my attempt at drawing a hook. You cannot find an injective function from S to P if m is greater than n. I have stated it for the concrete sets initial segment 1 to m and initial segment 1 to n, just so that you have some fixed sets in mind. The same proof that you have obtained will work even when S is an m element set, P is an n element set, and m is greater than n. Now the common way by which this pigeonhole principle is illustrated is by pigeons and holes. So what this says is, let's say you have holes where pigeons go and sit. If the number of pigeons exceeds the number of holes, then obviously if all pigeons are in holes, some pigeons have to share. It's usually illustrated this way. Okay. Now there are many amusing applications of the pigeonhole principle. For instance, you can use the pigeonhole principles to actually prove that there are two people in the city of Chennai who have exactly the same number of hair on their head. Now this is a completely amusing and useless thing, but you will know that this will be true for the city of Chennai. It might not be true for small cities, cities whose population is only 50,000 or so. It might not be true. So it's an amusing and fun, I would say, I wouldn't call it an application of the pigeonhole principle, but an amusing joke that follows from the pigeonhole principle. More seriously, you can use the pigeonhole principle to show facts in algebra. We will use it multiple times in this course. One of the major results, which we will not see in this course or in the follow-up courses also, says that a finite division ring is actually a field. I think it's called Wedderburn's little theorem. So it's one of the famous results that uses the pigeonhole principle. So you must not underestimate the pigeonhole principle. If by any chance you have a background in mathematical Olympiads, you will definitely know how useful the pigeonhole principle is in cracking questions from the Olympiad. So again, I will not give a proof of this. I hope you have done it yourself. If not, do it. Okay. Now we come to an interesting fact which I am going to prove. The set of natural numbers n, which is 1, 2, 3 dot dot dot, is infinite. Well, this seems completely obvious. There are 3 dots there, which means the set goes on endlessly. But we have a precise definition of finite and infinite, and we have to stick to that precise definition. Okay? So how do you prove something like this? Well, there is a bit of thought that needs to be done. The definition of infinite set that we have given is itself a negative definition. That means you say a set is infinite if it is not bijective to any initial segment 1 to n. So the definition itself is a negative definition. Immediately you must attempt a proof by contradiction. So let's try that. So let f from 1 dot 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 n to natural numbers. Now you might think what I am about to write next is bizarre, but I am doing it for a reason. Be a surjective function. Be a surjective function. I am going to show that this is not possible. So technically I have more at my disposal. I can reach a contradiction by starting with a bijective function, but a bijective function is surjective. I am going to show that there is no surjective function that is possible from 1 to n to natural numbers. So this additional little bit of flexibility that I get will prove to be useful in subsequent results. So I mean, this is a completely obvious thing to say. I am to defeat my opponent in a boxing match. If I am so good that I can do it with one hand behind my back, why not? I can show off. Okay. So let's prove this. Suppose there is a surjective function f from 1 to n to n. What you do is consider the maximum of the set f of 1, f of 2 dot 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 f of n. What do I mean by consider the maximum of f of 1, f of 2 dot 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 f of n? Well, I mean exactly what I say. The maximum of 2, you can define this max function. So if you want to be 100% rigorous and pedantic, of course there will be some amongst you who are 100% rigorous and pedantic. I am not going to say that you guys are not allowed to take this course. If you want to be 100% precise, what you have to do is you have to use recursion or some other form of definition to show that there is a function max n that takes as input n natural numbers and outputs a natural number. Okay, what it eats n natural numbers, and as output it gives you the largest natural number of those n natural numbers. Okay, so for every n there is a function called max n from natural numbers natural numbers power n to n. That is, it eats up n natural numbers and outputs the maximum of them. Now, it is a somewhat tedious exercise to show that such functions actually exist. For 2, if you just have 2 natural numbers, it's rather easy. You can say max of x1, x2 is x1 if x1 is greater than or equal to x2, otherwise it's x2, right? Now, if you want to define for n natural numbers, you can either keep using this same logic or you can use recursion. Think about how you can use recursion to define this function. Okay. Now, it does not matter how you do it, or if you have just completely ignored this part because it is a little bit of a exercise in pedantry, you can take it for granted that you have such a function. Given a finite set of natural numbers, there is a function that gives you the maximum of those finite number of natural numbers. Okay, let's call this finite number as m for maximum. Okay, then obviously m plus 1 is not in the image of f of 1 to n. This is obvious. That's how m was defined. So this is a technique that is going to be repeatedly used in many proofs to show that a particular function is not surjective. You sort of force an element by definition to be not there in the image. Here the forcing was rather trivial, but you get the gist. Now you should think about, does this really require a proof? And that too, I did spend a few minutes on this proof. Does this really require a proof, or can you just avoid a proof? Maybe it's just obvious from the definition. Please spend some time thinking about it and convince yourself that this theorem actually requires a proof. It's not obvious from the very definition that the set of natural numbers is infinite. Okay. Now, the next result is very, very interesting. It says a set S is infinite if and only if there is a proper subset that is also infinite. Well, if you have a finite set, let's say of n elements, then by the pigeonhole principle, any subset is of cardinality that is strictly lesser. We will show in a while that a characteristic feature of infinite sets is that infinite sets have proper subsets that have the same cardinality. This is one of the steps in the exercise to get to that proof. Okay, how do you prove something like this? A set is infinite if and only if there is a proper subset that is also infinite. Well, this is rather trivial. If you have a proper subset that is infinite, then the set S is infinite because supersets of infinite sets are infinite, as you would have shown by now. The other way is just one line. Suppose S is infinite, but S minus S1 is finite, where S1 is some element of S. So what I am doing is, I am starting with an infinite set S and I am saying pluck out one element and throw it away. I am calling that one element S1. Suppose after this throwing away, you are left with a finite set. Then that means you have a map F. Now of course, this removing one element from an infinite set cannot leave you with an empty set. That's obvious. So I'm going to completely ignore that case. I'm going to assume that there is a bijection F from 1 to n to S minus S1. That's what is the meaning of S is a finite set. It is bijective to some initial segment. So there is a bijection F from 1 to n to S minus S1. Well, now it's a triviality to construct a bijection G from 1 to n plus 1 to S. All you have to do is set F and G to be the same on the initial segment 1 to n and just set G of n plus 1 to be S1. Then you get a bijection. This is a bijection in an obvious way. So starting with a bijection from S minus S1, it's trivial to construct a bijection from 1 to n minus 1 to S. Okay? So this shows that if you have an infinite set, there is a proper subset that is also infinite. Okay. Now, the next characteristic feature of infinite sets. If S is an infinite set, then there is an injective function from the natural numbers to S. So in a sense, every set S has a copy of natural numbers, not merely as a set. Natural numbers come equipped with other features like the binary operation and all that, but just as a set, the natural numbers are sitting inside any other set S, provided S is infinite. Well, how do you prove something like this? I am going to give a proof that is going to open up a lot of questions. We do something obvious. What we do is the following. Let S1 be some element in S. Okay, let S1 be some element in S. Then what we have just shown is that S minus set with S1 is infinite. By the way, as I have mentioned, when you are removing just one element, sometimes out of laziness I might avoid writing the flower brackets. It's common convention that when you write S minus just a single element, you really mean S minus the set consisting of that single element. Okay. Now, this is a real abuse of notation because remember S1 itself is a set. So, there are two possible meanings that you can assign to it, but let me just reiterate that whenever you write S minus a single element S1, what you really mean is S minus the set with S1. Okay. So, we have just shown that S minus the set with S1 is infinite. So, let S2 be in S minus S1. And you can guess where this is going. You say having chosen S1, S2, Sn, choose Sn plus 1 to be some element in S minus S1 to Sn. Okay. You can always do this because we can repeatedly show that S minus set with S1 to Sn is a non-empty set. Therefore, there must exist an element Sn plus 1. So, an easy argument using induction will tell you that there exists a function f from natural numbers to S with f of n equals Sn. That is, to be more precise, because n is already coming into the picture, this might be confusing. Let me just say f of j equals Sj. So, you can repeatedly pick elements from the set S. You will never be able to exhaust it in a infinite time simply because the set S is infinite. So, you can construct this function with f of j equal to Sj. Now, what is this question that this proof asks us, or rather we ask after seeing this proof? Well, if you have a set S that is non-empty, then obviously there is an element S1 in S. That bit is obvious. Now, what I am saying is choose S2 in S minus S1. That is also obvious because we just showed S minus S1 is non-empty. The question is, even though the way I have written it, I am making a choice of Sn plus 1, having chosen S1 to Sn, what we are really asserting is that we can make infinitely many choices, right? To construct this function f from n to s with f of j equal to Sj, we have to repeatedly pick elements from the set S with some part removed. This is not, the fact that there is such a function f from n to s with f of j equal to Sj, this is actually not a consequence of any of the axioms that were listed some time before. We have listed only a subset of the axioms. You cannot use just that subset of the axioms to rigorously show that such a function exists. Now, I hope you are convinced at least intuitively how this function is born, right? You repeatedly just keep picking elements. You always have some elements left to pick because S is an infinite set. You can write down, or at least you can conceive of this function in your head. But If you want to be 100% rigorous, you have to invoke what is called the axiom of countable choice to in fact show that this function exists. But I do not want to engage in such great detour right away. Sometime in a future course, Algebra 2 or Algebra 3, we will actually eventually have to come to grips with the axiom of choice, because it will be needed in some of the major results. So up until then, I just want to postpone discussing the axiom of choice, but I hope you are at least convinced that there is a function f from the natural numbers to s. In this philosophical detour, maybe I missed something. Why is this function f injective? Please pause the video, think for a minute, and convince yourself that f is injective. Let me tell you why f is injective now. Well, it is by engineering, right? We engineered f in such a way that the value at j cannot possibly be any earlier value. Look at this, right? By this, we know that there is no possibility of f being non-injective. We have engineered it so that f is injective. Okay. Now we come to a major result that characterizes infinite sets. Infinite sets are special because if S is an infinite set, there is a bijection between S and a proper subset of S. This is a characteristic feature of infinite sets. Okay. In fact, this is sort of like an if and only if condition. The other side I am going to leave it to you to prove. It's rather easy for finite sets. You cannot find a finite subset that is bijective to the whole set. That's simply not possible. Pigeonhole essentially. Okay. This is a hard result. Why is it hard? Because the previous one is not really hard because we have some grip, namely the natural numbers. One of the sets is a known set. It's not an unknown set, it's a known set. Here, the only information you have about S is the fact that it's an infinite set. Apart from that, you have no information about the set S. So, how are we supposed to prove something about a set on which we have no grip, no way to hold the set? Well, we do have some grip. That's precisely what the previous result is, right? What you do is the following. By the previous result, by the previous theorem, we have a function, or rather an injective function, f from n to s. That's what the previous theorem tells you. Now what we are going to do is, our ignorance about the set S, we are going to make that immaterial by manipulating only the natural numbers. We have a good grip on the natural numbers. We are going to manipulate only with that. So, what I am going to do is, I am going to consider, so we have an injective function f from n to s. Let us consider, let us first prove the result for n. We are going to reduce proving this result for an arbitrary set S to proving it for the natural numbers. And the reason why we can do this reduction is because we have a bijection, not a bijection, an injection, f from n to s. Okay. So now what you do is consider the map from n to n minus set with 1. I am just going to remove 1. Well, the map is n goes to n plus 1. I have now constructed an explicit bijection from n to a proper subset, namely n plus 1, right. So now what you do is look at the set S. Inside this set S, there is a copy of the natural numbers. So let's call this map G. G is the map from n to n minus 1, n going to n plus 1. Okay. Inside this S, there is a copy of the natural numbers in the form of f of 1, f of 2, dot dot dot. Now what I claim is, I claim S is bijective to S minus f of 1, the set containing f of 1. Okay? I claim that there is a bijection from S to S minus the set with f of 1. So you might have already noticed I am using a little bit of loose language when really doesn't make sense to say S is bijective to S minus f of 1. That's just an elaborate shortcut to say that there is a bijection, so call it H, from S to S minus f of 1. That is, I am just abbreviating it and just saying S is bijective to S minus f of 1. Well, how do you construct this bijection? Well, I define it in pieces. H is from S to S minus set with f of 1, where H of S is just S if S is in capital S minus f of n. On the set which is not hit by the function f, I don't touch it. I leave it as it is. I leave it as it is. Okay. Then what I do is on I just set it to be f of so h of s is equal to f of, okay, let me just think for a second. What I want to do is, if S is equal to f of n for some n, then set h of s equals f of n plus 1. The motivation for this should be extremely clear, because we already have the bijection G from n to n plus 1. The motivation for setting h of s equal to f of n plus 1 comes from the fact that G from n to n plus 1 is a bijection. Now, the proof is technically not yet over. I have to show to you that h from s to s minus f of 1 is actually a bijection, but all the work has been done for you. All you have to do now is to sit calmly in a cool place and think for 5 minutes why this h is in fact a bijection from s to s minus f of 1. Okay? The whole thing has been constructed in such a way that this is going to be a bijection. Now, there is a fancy way to write down this function h using compositions. I am not going to do that. If you want, you can do that. That might make it easier to see that this is a bijection. So, the net upshot is the whole is not always larger than the part. You can have sets which have proper subsets which are bijective to itself. This is a peculiar and unique property of infinite sets. Okay. Now, here comes another mind-blowing fact. If S is a non-empty set, then there is no surjective function from S to the power set of S. Recall, this is the power set, the set of all subsets. set of all subsets of S. Okay. So that means the power set of S is always larger than the given set. Again, the proof of this is not straightforward, it's rather ingenious, and it's an idea that has unexpectedly dominated various parts of mathematics. Technically, it is called the Cantor's diagonal. Why it is called the Cantor's diagonal will be unclear in this proof, but as you study more and more courses, you will understand why it's called the Cantor's diagonal. Well, the proof is as follows. Suppose f from S to the power set of S is a bijection. Oh, sorry, surjective. It's a surjection. Now, what I am going to do is, I am going to force a set R to exist which cannot be mapped by F. That is, which is going to be there in the power set of S, but is not there. It cannot be there in the image. What do I do? Look at the set. Actually, I don't even need this to be a surjection. It's not a proof by contradiction. Okay, suppose this is a map. This is a map. I'm going to give a direct proof that F cannot be surjective. That's powerful. Okay, I'm going to show that F cannot be surjective. Well, what do? I construct this special set R, which is by definition those elements S in S such that S is not an element of its image. That's a bit mind-blowing. What I'm saying is, f of S itself is a subset of S. Either S is there in that subset or S isn't. I am collecting together those elements of S which are not contained in its image under itself. I sort of tripped over the tongue twister. I am collecting those elements S in S which are not elements of the image of F of S. Okay. Now, it is possible that this set is empty. Doesn't matter, the empty set is still there in the power set. It is possible that it is there in the empty set. R is the empty set. Well, suppose some S1, some f of S1 is R. Suppose f of S1 equal to R. Then there are two possibilities. The first possibility is S1 is in R. If you have R in the image of F, that is some f of S1 equal to R, then the first possibility is that S1 is in R. Well, that isn't possible, because if S1 is in R, then it cannot be in R. Why? Because R consists precisely of those elements S with S not in f of S, which means S1 cannot be in R, right? On the other hand, if S1 is not in R, then that means by the same logic S1 is in R. A contradiction, right? Hence, F is not surjective. Not surjective. Looking at this proof, I am tempted to go get a haircut. I hope you understood that reference, where we have seen this before. This is essentially Russell's paradox, essentially a variant similar to Russell's paradox, and the common way by which Russell's paradox is stated is using barbers. So please check Russell's paradox barber in your favorite search engine. You are in for a treat if you have not heard of it before. Okay. Now, the previous result says something interesting. Take the natural numbers. It's an infinite set, right? Yet, you cannot find a bijection to power set of n, right? Power set of n is a set whose cardinality is not the same as the cardinality of natural numbers. That means all infinite sets are not the same. Some infinite sets are larger than other infinite sets. That's mind-blowing. Because of this, there are things called uncountable sets. Power set of n is the first example of an uncountable set. A bit down the line, we will show that the real numbers which you have been studying for a long time are also uncountable. So, let's have the formal definition. We say a set is countable if it is either finite or has the same cardinality as the natural numbers. So, either the set should be finite or you should be able to find a bijection to the natural numbers. Then we say that the set is countable. Otherwise, we say the set S is uncountable. Uncountable means you cannot find a bijection to the natural numbers, nor is it a finite set. And there are examples of uncountable sets. Well, we have the power set of n. Okay. Now we come to an interesting point. Oh, by the way, I should at this stage make one more interesting point. Not only are there different sets of different infinite sets of differing sizes, there are infinitely many of them. What do I mean by that? Well, look at power set of n. Now that set has a cardinality different from the power set of n and different from n itself, right? So, by repeating this process, taking repeated power sets, you can see that there are a hierarchy of infinite sets. So, things start to get really mind-boggling. There are ladders of infinity. There is an entire ladder of infinite sets. And interestingly, it was a big problem to see if there is some set of intermediate cardinality between n and power set of n. That is, can you find a set which is larger than the natural numbers but smaller than power set of n? This was called the continuum hypothesis, and studying or trying to prove the continuum hypothesis led to great advances in the subject of mathematical logic. The people involved were Cohen and Kurt Gödel. Cohen is a Fields medalist. So, there is a lot of mind-bending stuff happening here, and I don't want to get into all of that because this is after all a course on algebra and not on set theory and logic. But if you are interested, I had referred to a book by Enderton multiple times before in earlier videos. You can have a look at that. Enderton also has a wonderful book on mathematical logic which is also worth looking at. Okay. Now, many sets of interest are countable, and how do you prove that a set is countable and how do you get a grip on countability? Well, countable sets are those whose elements can be listed. What do I mean by that? Well, let S be a non-empty countable set. The empty case is really trivial. Then either S is finite or there is a bijection from n to S. These are the only two possibilities. Okay? Either, to be more precise, S is finite includes S is empty. What I mean is S is bijective to 1, the initial segment 1n for some choice of n. In either case, it is clear that we can find a surjection F from N to S. Well, if there is a bijection from N to S, it's obvious that that bijection will work as a surjection. But if S is bijective to an initial segment 1 to N, how do you get a surjection from N to S? Well, I cannot pause the video. I do not have powers of telepathy or clairvoyance or any such thing. You will have to pause the video and try to figure out why, if S is bijective to the initial segment 1n, then there is a surjection from N to S. Please pause the video and think about that for a second. I hope you got how to get the surjection. All you have to do is start with the bijection from 1n to S. Then just pick your favorite element in S, set f of n plus 1 equal to that favorite element, f of n plus 2 equal to that favorite element, f of everything else to be that favorite element. In that way, you can easily construct a surjection from the natural numbers to S. Okay. Once you have this surjection, we can list down the elements of S as f of 1, f of 2, f of 3 and so on. So, if a set is countable, then you can do the same thing you have been doing for at least a dozen years. You can point out and say, this is the first element, this is the second element, this is the third element, except you may have to keep doing this motion forever if S happens to be an infinite set, but nevertheless it can be done, right? The question is the converse true? That is, if we can list the elements of a set, is the set countable? Well, you might think I'm crazy, isn't that obvious? You have already listed out the elements as f of 1, f of 2, f of 3, then the obvious bijection is available to you, right? Well, technically yes and no. Well, it is rather obvious, but a little bit of proof needs to be done. Okay. The precise statement is, if we can find a surjection from the natural numbers to S, that's what a listing really means, right? Then S is countable. Okay? Then S is countable. This is the precise statement of the converse. A listing is after all just a surjection. The technicality comes because the definition requires bijection, right? So, a little bit of work, teeny weeny amount of work needs to be done. If S is empty or finite, well, nothing to prove. Well, it's countable. So, we can assume S is infinite. Now, herein lies the technicality. You might think, well, I have a surjection from N to S, I just need to get a bijection, but the problem is this F could have repetitions. When you list out an elements, you can sometimes be careless. Well, it can't happen in an attendance roll in a class, each person is listed only once, but sometimes while listing you might list the same element 17 times, or maybe some element is listed an infinite number of times. So, we have to take care of that to construct the bijection. So, what we do is the following. We construct a map G from S to N that is injective. That is what we are going to do. We are going to construct G from S to N that is injective. How do we construct this G? Well, I define G of S to be the least element of F inverse S. Look at the pre-image of S, that's going to be a subset of the natural numbers. Look at the least element of that set, that is by definition G of S. Okay? Why does the least element exist? Well, because of the well ordering principle. Each F inverse of S is non-empty because F is surjective, and every non-empty subset of the natural numbers has a least element. Okay? So, check that G is injective. Well, that's obvious because F is a function, that's the reason why G is injective. Check that G is injective. So we have found an injective map G from S to N. Okay. Now we have still not yet done, right? We have still not yet done. We still have to show that we have a bijection. The problem is G could miss, or not could, will necessarily miss, some elements, of N unless F itself were bijective. This has to happen, right? If F were not bijective, that means there are at least two elements that F would have mapped, two elements of the natural numbers to the same element. One of those will be missed when you construct this G. Okay. How am I going to find out the required bijection? Well, rather easy. I prove another related result. Every infinite subset of N has the same cardinality, as N. Every infinite subset of N has the same cardinality as N. Well, I am a cheat. I am going to defraud you. I am going to give the same proof again for this. How? Well, let's call that set S. Let S be this infinite subset. Now what I am going to do is I am going to construct an explicit bijection H from the natural numbers to S. Okay. How am I going to do that? I am going to say H of 1 is least element of S, H of 2 is least element of S minus H of 1, and you can see where this is going. I define H of 3 as the least element of S minus H of 1 comma H of 2, the set consisting of those two elements, so on and so forth. Okay. This way you can easily see that H is a bijection. Okay. So any infinite subset of the natural numbers has the same cardinality as N. The original map G that we had is bijective to a subset of N, which in turn is bijective to N. So putting all together, you get the required bijection from S to the natural numbers. So seemed like a lot of work for something that you felt is obvious, but again, if you want to be 100% rigorous, you have to engage in some of this writing out the details. It's useful. Okay. So we see an application now. You might wonder why we spend so much time proving that result. We can show something interesting. If you have a countable set, if S is a countable set, and for each element S in S, you have a corresponding set Ts that is countable. That is, in the notation that we have introduced in an earlier video, we have an indexed family of countable sets. Then the union is also countable. The previous listing will allow us to give an extremely crisp proof of this fact. How are we going to show this? Well, what you do is let me move back to the older color. Let F from N to S be surjective. Well, whenever you have a countable set, you can list its element. So I have a surjection from N to S, right? Now let Gi from N to S be surjections from N to T of Fi. This is the toughest part. What you're really, the notation is making it look more complicated than what it actually is. There are three possibilities. S is itself empty, in which case this entire result is a trivial nonsense. I won't even be dealing with that case. Forget about it. S is a finite set. S is an infinite set. If S is finite, then you can essentially list out the sets T as T1, T2, T3, T4 up until Tn. If S is infinite, the list is slightly longer. It's T1, T2, T3, T4, T5, T6, T7, T8, T9, so on and so forth. It keeps going. Okay. What this function f allows me to do is to treat both cases in a unified way. If the set S happens to be finite, many TFIs will repeat, because how did we construct the surjection from a natural numbers to a finite set? Well, I said pick your favorite element in S and keep repeating after that. So there will be a lot of repetitions, but it doesn't matter at all. It is completely irrelevant. Okay. In a similar way, each TS is either empty, infinite or finite. Again, the empty case is completely trivial. You can in fact throw away all the TSs that are empty. They don't contribute anything in the union anyway. So technically this proof is incorrect, because I am not dealing with the cases where some of the sets could be empty, but dealing with those cases where some of the sets is empty is an empty exercise, so I won't even bother doing it. So each of these GIs essentially allow me to list the elements of TFI. Okay. So what I mean is, we can list out the elements of the first set TF1. I can list it out as G11, G12, G13 and so on. If TF1 happens to be finite, after a stage it will all be the same, it will be repetitions. Similarly, I can write TF2 as, technically I should put it as a set. TF2 is G21, G22, comma dot dot dot. And you can see where this is going. At TF3 is G31, G32, comma dot dot dot. Now I'm going to, you have this huge infinite array. If you know matrices, it's an infinite array of, infinite infinite cross infinite matrix. I have both ways an infinite grid. Okay. Now what I do is, I can construct a function h from the natural numbers to the union of T, what was the notation? Yeah, union of S and S, TS. Okay. I can now construct a bijection. Not a bijection, sorry, surjection. How do I construct that surjection? Well, there are many ways to do it. One particular way to do it is, first set h of 1 to be G11. Then set h of 2 to be G21. Then set h of 3 to be G12. And so on and so forth. How am I doing this? Well, I am setting h of 1 to be this value, G11. Then the next value is G21, the value after that is G12, then I'm going to set G31, then G22, then G13, so on and so forth. Okay. So the way that the listing goes is, I go like this, like this, like this, like this, like this. I exhaust the entire array. You should sit down and write out an explicit formula for H. It's not that difficult. I'm not doing it only because I'm lazy. Please write down an explicit formula for H. Now there are several other ways to traverse this array. You can sit down and think about other ways. Some of the ways might be easier to write down an explicit expression. Okay. Please do that. It's an interesting exercise to do. Okay. Once having done that, we have shown that the elements can be listed, therefore the union is a countable set. Okay. Now, this fact that union of countable sets which are themselves countable, right? Union of countably many sets which are themselves countable is very easy. Using this, you can easily show that the integers and the rational numbers are both countable. Okay, it's very easy to show using this. Okay, please do that. It's instructive. The Q case is particularly interesting. Just try to do it. That concludes this video on cardinality. If I got my timing right, this video is probably the longest video in this entire course, which is intentional because a video that discusses infinite sets and uncountable sets, if it is not really long, then where's the fun in that? So that concludes this long video. This is a course on algebra and you have just watched the video on cardinality of sets.